Welcome to The Explainer. Today, we are diving into the hidden chemistry that powers our world, from the sharp zing you get from a lemon to the simple relief you feel after a bee sting. Yep, we're talking about acids, bases, and salts.
So, what is the connection? Well, it's this powerful chemical trio: acids, bases, and salts. They're like these invisible agents behind so many reactions. And in this explainer, we're going to make sense of exactly how they shape our world.
All right, so let's jump right in with the two main players in this chemical story. What actually makes an acid, and what makes a base? Let's break it down.
So here's the deal. It all comes down to what they do when you put them in water. Acids release these hydrogen ions. That's what gives lemons their signature sour kick. Now, bases do the exact opposite. They release hydroxide ions. And that's why something like soap feels slippery and tastes better. You can literally see their opposing nature in a litmus test, where they flip the paper to completely different colors.
And get this, these aren't just some weird chemicals locked away in a lab. They are everywhere. That sharp taste in vinegar, that's acetic acid. The tang in your orange juice, you're tasting citric acid. And that painful little burn from an ant sting? Yep, that's methanoic acid doing its thing. This chemistry is happening all around us, all the time.
Okay, so short of tasting them, which is, by the way, a terrible idea, how do we tell them apart? Well, we use these little chemical detectives we call indicators to reveal their true nature. And there are basically three main types of these chemical spies. First, you've got natural ones, like turmeric, which you probably have in your kitchen right now. Then there are synthetic ones, which are cooked up in a lab. And this is really cool. There are even olfactory indicators that actually change their smell to tell you if you're dealing with an acid or a base.
And check out how they work in practice. Look at turmeric. It stays yellow in an acid, but put it in something basic like soapy water, and it turns it deep red. Or take phenolphthalein. It's totally colorless in an acid, but add just one drop of a base and boom, a vibrant pink. It's like a little chemical magic trick that reveals their identity.
All right, so now we know how to spot them. But what happens when acids and bases actually meet? This is where the real action begins.
The single most important interaction to know is the neutralization reaction. And it's named perfectly because the acid and the base literally cancel each other out. When they combine, they lose their old identities and form two brand new, totally neutral substances: a salt and good old water. Now, this is where things get really interesting. When an acid reacts with a metallic oxide, that's just a metal combined with oxygen, it also produces salt and water. So you see the pattern, right? If the end result is exactly the same as our classic neutralization reaction, what does that tell us about that metallic oxide? What role is it playing in this little chemical dance?
It means that the metallic oxide is acting like a base. This uncovers a really important rule in chemistry. Metallic oxides are basically bases in disguise. And you can flip that logic around. It also means that non-metallic oxides, like the carbon dioxide we breathe out, are acidic.
But you know, not all acids or bases are created equal. Some are incredibly strong, and others are really quite weak. So let's look at how we measure their strength. For that, we use the pH scale. It's a universal ranking system that goes from 0 to 14. A perfect 7, right there in the middle, is completely neutral. Think of pure water. Anything below 7 is acidic, and anything above 7 is basic, which we also call alkaline. But here's the kicker, the part that's easy to miss. The scale is logarithmic. That means a pH of 2 isn't just a little more acidic than a pH of 3, it's 10 times more acidic. That is a huge difference. And here's the key takeaway. The further you get from that neutral 7, the stronger the substance is. A pH of 1, like battery acid, is an extremely powerful acid, way stronger than milk, which sits around a pH of 6. And on the other side, drain cleaner at a pH of 14 is a much stronger base than something with a pH of 8.
Now, I know this might all seem a bit abstract, like something you'd only see in a science class, but the idea of pH is constantly and critically at work in our daily lives, and even inside our own bodies.
I mean, think about it. From the incredibly powerful acid in your stomach that helps digest your food, to the delicate pH balance in the soil needed to grow that food in the first place, pH is absolutely critical. Even keeping your teeth healthy is a constant battle against acids from the food you eat.
Let's take a common and pretty painful example. When a bee stings you, it's not just the poke that hurts, it's a chemical attack. The bee is injecting an acidic venom into your skin.
So we've all heard the old home remedy, right? put a paste of baking soda on the sting. But why does that actually work? What's the real chemistry behind that cure?
Well, it's because baking soda is a base. When you apply it, you're performing a tiny neutralization reaction right on your skin. It cancels out that acidic venom, and that's what brings the relief. It's a perfect, real-world example of everything we've been talking about.
Okay, for our last section, let's talk about the salts that get produced by these reactions. Because they're way more than just the stuff you sprinkle on your food. In the industrial world, they're absolute powerhouses.
A perfect example of this is a procedure called the chlor-alkali process. It sounds fancy, but the idea is actually pretty simple. You start with basic salt water, or brine, you pass some electricity through it, and you end up creating 3 incredibly valuable, totally separate chemicals.
And this is where it all comes together. The salts created from these simple reactions are transformed into so many essential products. We're talking caustic soda for making soap, baking soda for fire extinguishers, and even the plaster of Paris that's used to set a broken bone.
So, from the basic toothpaste you use to neutralize acids in your mouth, to the baking soda sitting in your fridge, this world of acids, bases, and salts is truly everywhere. The only question is, now that you know what you're looking for, which of these chemical reactions happening all around you will you notice first?